Hello, everybody. We begin a new topic in this course, generation-recombination processes in semiconductors. So previously, we have spent quite a few lectures discussing the equilibrium concentrations of electrons and holes, but what happens if a semiconductor is not in equilibrium? For example, if you have injection of electrons and holes at the point of contact, or if light is shining on the semiconductor, it is absorbed, it generates electron-hole pairs, then we are out of equilibrium. And how do we describe these situations? It is clearly a very important question. So today I will discuss, here is the outline somewhere of this lecture. I will discuss recombination processes. I will make a distinction between radiative and non-radiative recombination mechanisms and how they are important in direct versus indirect bandgap semiconductors, how they proceed, in these two types of semiconductors. Then I will introduce mathematical apparatus to describe charge carrier concentration dynamics in the presence of non-equilibrium excitation. And finally, I will introduce a very useful approximation called the relaxation time approximation, which considerably simplifies the charge carrier dynamic equations or kinetic equations in the low injection limit. All right, so let's begin. Now, a recombination process, when we were discussing semiconductors and equilibrium, what exactly did we mean by equilibrium? So common sense suggests that an equilibrium is when nothing changes. Like you put something on a surface and it doesn't move because it has reached equilibrium position. Or even better, you put something in a box and it doesn't move because there are walls that prevents that object from getting out. So in physics of many body systems, this is not how we understand equilibrium. Actual equilibrium is a pretty wild state where everything changes. Things do change. Particles move left and right. They interact, they exchange, they collide with each other, they exchange energies. But on average, nothing changes. The number of particles that move from point A to point B is perfectly balanced by the number of particles that move from point B to point A per unit time. That's what we mean by equilibrium. When we were talking about charge carrier concentration in equilibrium, we didn't mean that an electron that moves from the valence band into the conduction band stays in the conduction band forever. No, that electron can move back into the valence band. So there are two counter-directed currents, so to speak, current of electrons from valence band to the conduction band, and also a counter-directed countercurrent from the conduction band into the valence band. But in equilibrium, the two processes mutually cancel. We call these two processes generation and recombination. And in equilibrium, only one type of generation, that is production of electrons, promotion of electrons from the valence band to the conduction band, only one type of this generation processes is present, and this is the thermal generation. But nobody says that only thermal generation is acting in real life. In fact, in real life, like I said earlier, current may be flowing, light may be shining on the semiconductor. So you can have other non-thermal generation processes. Now, the counter process is called recombination, when an electron goes back from the conduction band to the valence band. Or you can say that when an electron meets a hole and they mutually annihilate, this is recombination. Now, when a recombination process happens, energy gets released. That energy is fairly high. It is of the order of bandgap energy, so 1, 2 electron volts, like depending on the bandgap value. So it's fairly high compared to what? Compared to thermal energy. Also, some momentum gets released because the momentum of the electron and the hole, they do not necessarily add up to zero. So there is some momentum and both energy and momentum which are released in a recombination away, they need to be taken away, carried away by someone, or something, by some particle. And you can have two possibilities, two kinds of particles that can do this. Either it can be a photon or something else. And that something else can be typically like it can be a phonon, quantum of lattice vibrations, or it can be another electron, or it can be another hole. So correspondingly, we distinguish between radiative and non-radiative recombination processes. In radiative recombination, it is the photon which carries away the extra energy and momentum, a little bit of momentum. And in non-radiative processes, it is something else, not a phonon, but something else which carries away this energy and momentum released in a recombination event. So first, let's think a little bit about this radiative and non-radiative recombination a little bit more. So let's say the energy that is released is of the order of 1 electron volt. It's the band gap energy. What is the momentum of an electron which has this energy? What is the momentum of a photon which has this energy? Well, the momentum of a photon with the energy E is by what we have learned from quantum mechanics, it is energy divided by the speed of light, because that's the energy momentum relation of a photon. Because energy is Planck's constant times frequency, and momentum is Planck's constant divided by the wavelength, and wavelength and frequency are related by the speed of light. So as for electrons, the kinetic energy of an electron is momentum squared over twice the electron mass. So the momentum is square root of twice the electron mass times the energy. So let us take the ratio of the momenta of a photon and of an electron, which provided that they have the same energy E of the order of the band gap energy. Now we have for the photon E over C in the numerator. For the electron, we have square root of 2 electron mass times energy E, which we can rewrite as square root of energy divided by twice the electron mass times C squared. Now, the product electron mass times C squared, of course, you remember probably the most famous equation of Albert Einstein, E is mc squared. This is the so-called rest energy of an electron. The rest energy of a particle is its mass times C squared. The rest mass times C squared. Now, the rest mass of an electron is 511 kilo electron volts. Twice that value is more than 1 mega electron volt. 1.022 mega electron volt. Mega is 10 to the 6. Whereas the energy released in the recombination event, this energy E, is the band gap energy of the order of 1 electron volt. So the ratio is 10 to the negative 6. The square root of that ratio is 10 to the negative 3. Okay, so a photon with an energy E of the order of 1 electron volt carries momentum which is about 1,000 times smaller than an electron with the same energy, than the momentum of an electron with the same energy. What can we conclude from this estimate? We can conclude that if the semiconductor is a direct band gap semiconductor, like gallium arsenide, then the top of the valence band happens to be at the same quasi-momentum as the bottom of the conduction band. And hence the energy, the momentum released in a recombination event is practically zero. Whereas in indirect bandgap semiconductors, where the band extrema, the top of the valence band and the bottom of the conduction band, happen at different values of the momentum. And so considerable amount of momentum is released in a recombination event. So, and the photon cannot carry away that momentum, because a photon of the energy of 10 to the negative of 1 electron volt carries very little momentum as compared, for example, to an electron. Or so you need a third particle. You need a third particle in indirect bandgap semiconductor, not just electron and hole, which is an absence of an electron. Okay, so let's count an electron and hole as a single particle, plus a photon, plus a third particle that would carry away that momentum, that extra momentum. So in direct bandgap semiconductors, radiative recombination is something that cannot be switched off, and it will proceed at a much higher rate. It will be, in fact, it will be a dominant recombination mechanism in direct bandgap semiconductors than in indirect bandgap semiconductors. Why the probability of radiative recombination in indirect bandgap semiconductors is much smaller? Because in order for a recombination to happen, you need an electron and a hole and some other particle, typically a phonon. They need to meet together in order for the phonon to carry away that extra momentum. So the more particles get involved in the process, the less likely the process is. All right. Okay, so that's the take-home message of this slide. Radiative recombination proceeds much more frequently, much more likely in direct bandgap semiconductors than in the indirect bandgap semiconductors. But by the way, since you cannot switch off the radiative recombination, even in indirect bandgap semiconductors, phonons can be produced as well. There nothing speaks against this possibility. This kind of recombination, radiative recombination, from this slide, is the so-called intrinsic recombination mechanism, not to be confused with intrinsic carrier concentration. It is called intrinsic recombination mechanism. Another intrinsic recombination mechanism, that is the one which cannot be switched off, is the so-called Auger recombination, named after the French physicist Pierre Auger, who lived about 100 years ago. So initially, Auger processes have been described in the theory of X-ray interaction of X-rays with atoms, but a similar mechanism happens in semiconductors. So this is what happens. Let's say you have an electron, you have a hole, they recombine, and the extra energy and momentum are carried away by another electron or another hole. So this is the upper diagram. Electron meets a hole, they recombine, and an electron from the conduction band gets extra energy of the order of bandgap energy. It becomes very hot. It becomes a hot charge carrier. And then it fairly quickly, it dissipates this extra 1 electron volt or so of energy by exciting the lattice vibrations of the crystal lattice, by exciting the phonons. So this is the electron-mediated process. Or you can have a hole-mediated Auger recombination process when an electron meets a hole and the extra energy is given to a hole which goes not up but down on the energy scale. So this is how we think of we can think of it, like a hole sees the energy kind of upside down, right? But in reality, the extra energy is, of course, given to an electron from well below the top of the valence band. That electron goes up to the top of the valence band, and a hole is produced somewhere 1 electron volt below the top of the valence band, in the valence band. So this is what happens in reality. But I like the hole-based language a little bit better because it is fun. So and then of course that hole goes back to the top of the valence band from here, from a state somewhere 1 electron volt below the top of the valence band. It goes back to the top of the valence band, and as it does, it dissipates again. It dissipates energy into the lattice vibrations, into the phonons. All right, so Auger recombination is another mechanism which cannot be switched off by any means. You always have some electrons, you always have some holes, and those extra electrons and holes can always carry away the energy and momentum released in a recombination event. Now, there are also extrinsic recombination channels, the main are the so-called Shockley-Reed hole recombination. So you have already heard that name, Shockley, William Shockley. Couple of lectures ago. And the second one is surface recombination. So these are the extrinsic recombination channel, and by extrinsic we mean that they can be controlled, at least to some extent, by increasing the purity of the semiconductor, or by applying surface passivation techniques, special surface passivation techniques. So here is what happens. So we have discussed, you remember, the donor and acceptor impurities are called shallow impurities, in the sense that their energies are close to either conduction band edge energy or valence band edge energy, shallow impurities. But then there are also deep impurities. These are typically impurity metals, like iron, like copper, like I do not know, even gold and platinum are found in very small quantities, like maybe 1 out of 10 to the 15th atoms is maybe a gold atom. So a small admixture of typically metallic foreign atoms, which are in the crystal lattice, and an electron can be bound and be captured by such an atom, creating a localized electron state. So this impurity atoms, the deep impurities, are called deep because the energy of a captured electron is somewhere in the middle of the valence band. Oh, sorry, somewhere in the middle of the band gap. In the middle of the band gap, of course. So deep impurities are bad. Shallow impurities are good, and deep impurities are typically bad, because a deep impurity can, they act as traps. Those deep impurities are traps for electrons. So a deep impurity can trap an electron from the conduction band, capture in the process called electron capture, and it can release that electron into the valence band in the process called hole capture. Or you can think of the release of an electron into the valence band as capturing a hole from the valence band. Now, of course, the deep impurity can also release an electron back into the conduction band, which is electron emission, or it can release a hole, or it can capture an electron from the valence band. In other words, it can emit a hole into the valence band, hole emission. And the theory of Shockley-Reed-Hall recombination is, I wouldn't say that it is overly complicated, but the final result of that theory is so simple that I decided not to include the theory of Shockley-Reed-Hall recombination into this lecture course. But of course, you can read about Shockley-Reed-Hall recombination theory in any textbook on semiconductor physics. It is quite standard. I will talk about the main result of the theory of Shockley-Reed-Hall recombination, but for now, let me just say that the final result is fairly simple for our purposes. All right. So, and that theory, it discusses the balance between these four processes: electron capture, electron emission, hole capture, and hole emission. And in the end, it produces something called the Shockley-Reed-Hall recombination rate. So surface recombination proceeds in a way which is similar to the Shockley-Reed-Hall recombination mechanism. Only the recombination centers are not in the bulk of the material, they are on the surface. And the surface concentration of the recombination centers is fairly high, typically, because this can be various lattice defects on the surface, dangling bonds on the surface, impurity atoms on the surface. So you can control the rate. Of course, you want to make the recombination rate as small as possible. You can control the Shockley-Reed-Hall recombination by trying to make your semiconductor as impurity-free as possible. Now, this is, of course, the goal which is not so easy to achieve, but there are special technological processes which allow you to make the recombination rate due to Shockley-Reed-Hall mechanism very small. So the lifetime of your charge carriers can be as high as, let's say, 10 milliseconds. It's a very long lifetime. Now, surface recombination is we also want to minimize surface recombination, and this is done by passivating the surface. So covering the surface with various materials that minimize the number of recombination centers per unit surface area, and also that result in a band bending such that you have, for example, mostly electrons or mostly holes near the surface. And in order for a recombination to happen, you need both types of charge carriers, both electrons and holes. All right. So next, charge carrier dynamics. Now it's time to discuss how to describe recombination processes mathematically. First, I would like to introduce the non-equilibrium excess carrier concentration, delta N. It is the difference between the actual concentration of your electrons from the equilibrium concentration, or of your holes from equilibrium concentration. So in this discussion, I will assume that the material remains electrically neutral. That is, for each. So equilibrium electron and hole concentrations are related by the charge neutrality condition. Equilibrium concentration of electrons plus the concentration of ionized acceptors, which are negatively charged, equals the equilibrium concentration of holes plus concentration of ionized donors, which are positively charged. And now in non-equilibrium situations, you have extra charge carriers, excess carriers, whose concentration is denoted as delta N, and you want to have as many excess electrons per unit volume as excess holes per unit volume in order for the whole structure to be electrically neutral. So let's call delta N the excess carrier concentration, and the non-equilibrium concentration of electrons N is the equilibrium value, N naught plus excess value delta N, and similar for holes. P is P naught plus delta N. Now let me introduce the generation rate. The generation rate, typically denoted with the letter capital G, is the number of electrons and holes, electron-hole pairs, which are produced per cubic centimeter per unit volume, right? Per 1 second, in 1 second, per unit time. So the generation rate is measured in inverse cubic centimeters, inverse seconds. How many electron-hole pairs are produced per unit volume per unit time. And we need to distinguish between the thermal and non-thermal generation rates. Thermal generation rate cannot be turned off. The non-thermal generation rate, typically it is when light is shining on the material. So photons get absorbed, electron-hole pairs get produced. Thermal generation rate is predominantly due to the interaction between electrons from the valence band and phonons. Now, typically the energy of a phonon is maybe a few times, 2 or 3 times bigger than the thermal energy. So typical phonon energy is not more than, let's say, 1/10 electron volt. But phonons are distributed in energy. So there is a tail in that distribution which contains phonons whose energies are comparable or bigger than the bandgap energy. And it is those hot phonons which result in the generation of electron-hole pairs, that is, in the promotion of electrons from the valence to the conduction band. So this is the thermal generation rate. And like I said, the non-thermal generation rate proceeds typically through the absorption of light, absorption of photons, which come from the outside world. And also you can inject electrons or holes into the material at the point of contact, like your semiconductor is part of some circuit. So injection and current is flowing, so that's another reason for non-thermal generation. Now, I would like to, we also need another rate, that is the recombination rate. The recombination rate tells me how many electron-hole pairs recombine per unit time in a unit volume. Okay. So these are the parameters that our theory will be using. Excess carrier concentration, delta N, generation rate, which contains of the thermal and non-thermal contributions, and the recombination rate. The thermal generation rate does not depend, the thermal generation rate does not depend on the concentration of charge carriers. In fact, the non-thermal generation rate also does not depend on the concentration of charge carriers, typically. But the recombination rate does depend on the concentration of charge carriers because if you double the number of electrons per unit in conduction band per unit volume and double the number of holes, then it is intuitively clear that this will result in an increased recombination rate. of the two types of charge carriers. All right. So here are this. So here is the main equation, the kinetic equation that describes the dynamics, the time development of the excess carrier concentration. The rate of change, so excess carrier concentration tells me how many excess charge carriers I have in a unit volume, in cubic centimeter. The rate of change of delta n, excess carrier concentration, is just the balance between the generation and recombination rates. So generation rate minus recombination rate. Now, the difference between the recombination rate, R, and the thermal generation rate, which is fixed at a given temperature, is called the net recombination rate. And the advantage of using the net recombination rate is that it is zero, the net recombination rate, U, it is zero when you are in equilibrium. That is, when delta n goes to zero. And then you are in the equilibrium situation, and there is no disbalance between the generation and recombination processes. The net recombination rate goes to zero. The net recombination rate can become negative. It only means that there is some mechanism, but other than the thermal generation, in which the charge carriers are produced in the material. So here we go. d delta n by dt is the difference between the non-thermal generation and the net recombination rates. In thermal equilibrium, the non-thermal generation is zero, delta n, the excess carrier concentration, is zero, so the rate of change of the excess carrier concentration is also zero. The only generation that you have is the thermal generation. And so the net recombination rate at zero delta n is zero. So the thermal generation rate can be identified with the recombination rate R at zero excess carrier concentration. G thermal is R of zero. Next, I would like to introduce a useful approximation which is valid when your excess carrier concentration is small, delta n is small as compared to the equilibrium concentration of majority carriers. This is the recombination time approximation. So let us assume for now that the non-thermal generation is off, no light is shining, and maybe light was shining before, but then at the time t equals zero, you have switched off the external source of light, and your excess charge carriers recombine. They do not recombine immediately, but they do recombine, and so over time, the concentration of excess charge carriers should go to zero. So how do we describe this process, and how does it go to zero? We assume that originally the initial value of the excess carrier concentration was not very large. In that case, we can expand the net recombination rate, delta n, in the first order of delta n, if delta n was not very large. Now, this expansion is the so-called Taylor expansion. We have discussed Taylor expansion already, and we choose, it is a linear approximation of a function, u of delta n, where delta n is the argument. The parameters in that linear approximation are such that we correctly reproduce the value of the function u when delta n is zero, and we also want to correctly reproduce the first derivative of this function at the origin delta n is 0. So this is this linear approximation. When you set delta n to 0, you get u of 0 equals u of 0. We assume that u of 0 is known, and it is known because it is 0. U of 0 is 0. And the first derivative, u prime of 0, is also assumed to be known. The inverse first derivative of the net recombination rate at 0 excess concentration, so in equilibrium, is called the recombination time. So tau is 1 over u prime of 0. Again, prime indicates the derivative of the net recombination rate with respect to the excess concentration delta n taken in the equilibrium situation when delta n is set to 0. So this is the recombination time approximation. Within the recombination time approximation, the kinetic equation for the excess carrier concentration assumes a very simple form. The time derivative of the excess carrier concentration is negative excess carrier concentration delta n divided by the recombination time tau. And given the initial condition, that is, given the value of the excess concentration delta n at time t equals 0, we can solve this equation. The solution is just an exponential function, delta n of 0 exponential to the power negative t over tau. So indeed, if you set t to 0, you get delta n of 0 equals delta n of 0 because c to the power 0 is 1. And the derivative is d delta n by dt is delta n of 0 times negative 1 over tau exponential minus t over tau, which is negative delta n of t divided by tau, which is the right-hand side of this kinetic equation. This discussion has been done under the assumption that the non-thermal generation is 0. What if light is shining, so non-thermal generation is not 0? Then our kinetic equation has this non-thermal generation rate in the right-hand side. We have this initial condition, delta n 0 is the initial value of the excess carrier concentration. And first of all, it is clear that eventually the system will reach the steady state in which the non-thermal generation and the net recombination rates mutually cancel. And in that steady state, the excess carrier concentration will have some non-zero value, but it will not change in time. So the time derivative of the excess carrier concentration is 0. So we can find the concentration in the steady state by simply setting the left-hand side of this kinetic equation to 0. And we find that delta n in the steady state is just the product of the non-thermal generation rate, for example, due to light, and the recombination time tau. So now we can rewrite the right-hand side of the kinetic equation in terms of the steady state concentration by simply replacing the non-thermal generation rate with the steady state excess carrier concentration delta n steady state, delta nss. Now this is what we get, delta n steady state minus delta n over tau in the right-hand side. And but delta nss, the steady state excess carrier concentration, is a number. Its time derivative is 0. The time derivative of a fixed number is 0. So we can replace the time derivative d delta n by dt with the time derivative of the difference, delta n minus delta n steady state. D delta n minus delta n steady state by dt is negative delta n minus delta n steady state over tau. And now we can solve this equation for the difference of delta n and delta n steady state. And we get the exponential function. Now plug in the initial conditions. So at the initial time, we should have delta n naught minus delta n steady state at t equals 0. And this gets multiplied with exponential minus t over tau to get the difference between the excess carrier concentration and the steady state value at any time t. And so now we can solve for the excess carrier concentration, delta n, at any future time. Just add delta n steady state to the left-hand side and the right-hand side of this equation. All right. So that's yes, that's all for today. What we have not discussed yet is how to express the recombination rates in terms of the concentrations of charge carriers, how to find this recombination time tau. These very important and interesting topics will be covered in the next lecture. For now, thank you all very much for your kind attention and goodbye.